Hello student, welcome back. Digital Image Processing, Shongita Roy, Assistant Professor, Electronics and Communication Engineering Department, Narula Institute of Technology. Today's topic, Digital Image Restoration, Image Inverse Filtering. This is under Digital Image Restoration. Estimating the degradation function, there are three principal ways to estimate the degradation function for use in image restoration. 1. Observation, 2. Experimentation, 3. Mathematical modeling. These methods are discussed in the following section in detail. The process of restoring an image by using a degraded function that has been estimated in some way sometimes is called blind deconvolution, due to the fact that the true degradation function is seldom known completely. Now this is already we have studied that image recovery is a complicated process. It is associated with both multiplicative as well as additive, some noise or other parameters, degradation parameters. So if we leave the noise parameter, that we know the noise parameter or there is no noise at all, therefore there is degradation function. It is multiplicative in nature. So how to get back the original scenario or original image, that is F approximation UV in the frequency domain. Therefore F approximation UV is equal to GUV by HUV from the previous equation already we have discussed in the previous lecture. So F approximation is equal to GUV by HUV when noise we are considering almost zero. Therefore, it is not exactly the original FUV. Therefore, there should be some relation between F approximate UV and FUV. Therefore, FUV is equal to FUV plus the noise function divided by transfer function. This is the reality. Therefore, this is the second part of this equation, that is to this. This is the main criteria, that is our creating the main problem. So we have to find out this. Now exactly if we can observe very carefully, see the denominator, the transfer function is in the denominator. Now, at the time of designing FIR filter, or it is nothing but a kernel, a filter, so there are some coefficient of the filter are so that this value becomes 0. So the trouble comes from there. 1 by 0 or anything, some value divided by 0, creating problem at the time of differentiation or partial differentiation or any other type of mathematical modeling, because this is infinite or undefined. So design should be taken carefully so that there should be no such coefficient or value that will come or making this value equal to 0. This is the main challenge of image processing or any other mathematical modeling. Now this is showing original clear image. It is a sample image. Now this is how this is degraded. This is a degradation using a full filter. Now this is with a kernel of 40. This is a kernel of radius 70. This is a kernel of radius 85. Therefore, it is clear that if our original image is degraded, then the recovery of the image is depend on the kernel of the filter. Therefore, if the kernel is full, this is the output. It is unable to viewing. These two images are totally different. We are unable to view anything. Now it is little bit of viewing is there, but not complete viewing is it is there. So it is a partial viewing. Now the radius with 70, it is clear viewing. Radius with 85, totally unable to view anything. So kernel design is an important thing. Optimization or very critical optimization techniques or any modeling should be there. Now, minimum mean square error filter or Whiner filtering. The inverse filtering approach discussed in the previous section makes no explicit provision for handling noise. In this section, we discuss an approach that incorporates both the degradation and statistical characteristics of noise into restoration process. The method is founded on considering image and noise are random variables, and the objective is to find an estimation of the uncorrupted image F such that mean square error between them is minimized. Therefore, what we got in the previous this is the estimation of original image, and it is the original image. Therefore, these two should be as close as possible. Therefore, estimation of error is equal to F minus F approximation whole square E square should be as low as possible. Therefore, this error should be minimized. The estimation is the expected value of the argument. It is estimated that the noise and the image are uncorrelated, that one or the other has to mean, and that the intensity levels in the estimate are a linear function of the levels in the degraded image. Based on these conditions, the minimum of the error function is given in the frequency domain expression given by this. Now, this is the kernel, this is the mathematical model of this Whiner filter. This result is known as the Whiner filter after N. Whiner 1942, who first proposed the concept of the filter, which consists of the terms inside the brackets, also is commonly referred to as the minimum mean square error filter or least square error filter. Now, this is the original image. This is a Whiner filter image inverse filtering, and this is inverse filter radial image, and this is Whiner filtered image. This is Whiner filter, it is radial inverse filter, and this is full inverse filtering. This is the references, and thank you.